Good morning to one and all present here. Myself, N.S. Mohan, Assistant Professor for the Department of Mechanical Engineering, working at E-Road Sengundar Engineering College. Okay, and in today's topic, we are going to discuss about metal matrix composites and its manufacturing methods. And in the previous classes, we were talking about what are the different types of matrices, composite materials available. And it falls under three major categories, that is polymer matrix composites, the next is metal matrix composites, and finally we have ceramic matrix composites. And as I said in the previous class, we were discussing about polymer matrix composites in detail and also its manufacturing methods. And in today's class, we are going to discuss about metal matrix composites, their properties, and also the manufacturing methods. Okay, let us move on to the next slide. First, let us discuss about the introduction of metal matrix composites. So, metal matrix composites are either in use or prototype for the space shuttle, commercial airlines, electronic substrates, bicycles, automobile, golf clubs, and a variety of other applications. And it is most widely used in, especially in the case of uh, airlines and automobile industries. And while the vast majority are aluminum matrix composites, a growing number of applications require the maximum properties of superalloy titanium, copper, magnesium, or iron. So these are the major constituents that forms the metal matrix. Okay, I'll repeat once again. So it is aluminum matrix composites. It has a highest application limit when compared to other metal matrices. So, like all composites, aluminum matrix composites are not a single material, but a family of materials whose stiffness, strength, density, and thermal and electric properties are all of the properties are very good in this case of aluminum matrix composites, and that is why we are choosing aluminum as a base metal. Predominantly, we will be using aluminum matrix composites as your base material. That becomes your matrix. Okay. So superalloy composites reinforced with tungsten alloy fibers are being developed for components in jet turbine engines that operate the operation temperature is above 1830 degrees Celsius. So from this point, we can clearly understand why we are going in for superalloy composites, because the temperature withstanding ability, I mean the refractoriness of the product that is developed by processing your metal matrix composite, it becomes highly temperature resistant material, and that is why it is capable of withstanding a heat up to 1830 degree Fahrenheit. The next thing is properties of MMCs. MMC is nothing but metal matrix composites. So let us discuss about what are the various properties that are available in a metal matrix composite. The first thing is high strength to density ratio. So it provides a high strength when compared when the ratio is compared with density. Okay, so the density is nothing but your packing of the individual atom is your density, and it provides a better strength. And the next thing, we have higher stiffness to density ratios. It provides a great stiffness also, and better fatigue resistance. It's also resistance to fatigue. Better elevated temperature properties. As I said in the previous slide, it has a better temperature. It becomes a better temperature resistant material. So it has high strength and low creep rate. Creep rate is nothing but the crack propagation rate is also very less when compared to um, other types of composite material, and it has lower coefficient to thermal expansion and also better wear resistance. Then we have some advantages of MMCs over polymer matrix composites. So this here it is compared with your previous topic, that is polymer matrix composites. So let us discuss what are the advantages that we are having in the case of metal matrix composites. So high temperature withstanding capability, repeatedly it is coming, so it can withstand a high temperature when compared to that of polymer matrix composites. Since polymer is nothing but your plastic cannot withstand a higher thermal, higher temperature, and that can be eliminated with the help of using a metal matrix composites. And the next thing is it is fire resistance, higher transfer stiffness and strength, no moisture absorption. There is moisture absorption is completely eliminated in the case of metal matrix composites. Higher electrical and thermal conductivity. It is prone to high electrical and thermal conductivities. Better radiation resistance. It is also resilient to your radiations also. and no outgassing. It does not emits any gas from it. And fabricability is nothing but it provides flexibility in fabrication methods, and fabricability of viscous and particularly reinforced MMCs with conventional metalworking equipment. So here we can, in this particular point, we can see that what are the major advantages. We can use conventional metalworking equipment um, for fabricating your metal matching composites. So we have some disadvantages also here. Some of the disadvantages of metal matrix composites compared to monolithic metals and polymer matrix composites are listed here. So higher cost of some material system. So some materials, for example, say for example, aluminum cost is also high nowadays. So when compared to polymer matrix composites, we have to spend more on metal matrix composites, and it is relatively immature technology. Immature technology is nothing but it's just a booming technology. It is not. It has not established it. The establishment is not as good as like your polymer matrix composites in this case. And complex fabrication methods of fiber reinforced systems. So here the fiber reinforcement is quite complicated when compared to the tough polymer matrix composites. In polymer matrix composites, you can add fibers in any form, but in metal matrix composite, it requires an artificial method of manufacturing fibers here. And also the last point states that limited service experience. So people are nowadays doing experiments related to metal matrix composites. So as I said before, it is not an established method of manufacturing manufacturing matrices. Okay. So, and what are the reinforcement available in the case of metal matrix composites is listed here. So, reinforcement, MMC reinforcement can be divided into 5 major categories here. So, we have continuous fibers, discontinuous fibers, viscous, particulates, and wires, with the exception of wires, which are metal reinforced generally or ceramics. So, here the matrix will be your metal, whereas your reinforcement, whatever you are adding as your reinforcement is considered to be as a ceramic material. Okay, so and we have an artificial method of producing fibers in this case of in the case of metal matrix composites. So we have some key components of composites over here. The metal matrix composites and their key composites are listed here. Numerous metals have been used in matrices. The most important have been aluminum, titanium, magnesium, and copper. Okay, so if you are taking metal matrix composites as your area, you have to choose only these metals. So these metals is predominantly chosen for producing a component with other for other applications. The most important MNC systems are aluminum matrix. So let us just see what are the types of reinforcement available over here. So in the case of aluminum matrix composites, we have continuous fibers like boron, silicon carbide, alumina, graphite. These are the forms of continuous fibers, and in the form of discontinuous fibers, we have alumina and silica we are having, and in the case of viscous, we have silicon carbide. Silicon carbide is available in the case of viscous, and also in particulates, either in powder form or in granular form. We have silicon carbide and boron carbide. We have, and coming to the magnesium matrix, in the case of continuous fibers, we have graphite and alumina. Sorry, and in case of viscous, we have silicon carbide. Particulates, we have silicon carbide and boron carbide. So in the case of titanium matrix, we have continuous fiber, silicon carbide coated with boron, and particulates we have titanium carbide. So this is quite costly when compared to that of your previous things. Okay, so titanium becomes a much costlier thing. And copper matrix we have continuous fibers, graphite, silicon carbide. Wires we have niobium, titanium, and niobium tin we have. And in case of particulates, silicon carbide, boron carbide, titanium carbide, and other things. And in the case of super alloy matrices, we have tungsten. Okay, so tungsten is not that much helpful to you because it requires much more. It is much more expensive when compared to the previous things, that is copper matrix or titanium matrix. Then tungsten is compared to those metals. Tungsten becomes your highest, expensive one. So, and we have rule of mixtures in MMC composites. We have a specific rules over here in order to produce a component when you are choosing metal matrix composite. So here we have a definition for rule of matrix. A rule of matrix is a method of approach to approximate estimation of composite material properties. So here we have to do an approximate estimation before choosing your metal matrix. Okay, so the rule of mixtures comes like this. The rule of mixtures is a method of approach to approximate estimation of composite material properties based on the assumption that a composite property is the volume weighted average of the phase. Phase is nothing but matrix and disperse phase properties. Okay, so what we are going to do is what matrix you are going to take. Okay, and what are the amount of matrix you are going to mix with your reinforcement. That estimation has to be done well in advance before producing a component in this particular case. Okay, so according to the rule of mixture, properties of composite materials are estimated as follows. So we have to consider these properties when going in for role of materials. The first thing is density. Density is nothing but your packing. Okay, so packing has to be considered, and coefficient of thermal expansion. And when your particular thing is subjected to heat, the expansion has to be calculated before, and modulus of elasticity, how much elastic property does it have, that has to be taken into account. And we have shear modulus, Poisson ratio, and tensile strength. So these things has to be considered before mixing your matrix with before mixing your reinforcement with your matrix. Okay, so this is the rule of matrix here. So let us see the factors influencing the characteristics of MMC. So there are some typical factors that are influencing the characteristics. Let us discuss one by one. So reinforcement properties, form, and geometric arrangement. Reinforcement properties is nothing but the reinforcement, whatever you are choosing as reinforcement, those things properties has to be completely studied. So these are the properties that we discuss. Your density, coefficient of thermal expansion. These things has to be has to be estimated well in advance before taken into account for your manufacturing method. Okay, then the form in which form the reinforcement has to be added. Either it may be a particulate, it may be flakes, or it may be a discontinuous fibers or a continuous fiber. So what form you are going to use, that has to be taken into account. And geometric arrangement. Geometric arrangement is nothing but in what geometry you are going to produce the component. Okay, arrangement is nothing but the reinforcement. You are adding the reinforcement in reinforcement is nothing but it's not going to occur in a natural manner in the case of metal matrix composite. So what you are going to do is you have to arrange it by manual methods, that is artificial methods. So the arrangement has to be considered before going in for manufacturing of composite. Okay, so reinforcement volume fraction. Volume fraction is most what to say, it's the most important thing in this case, because the volume of reinforcement has to be considered. Why means if the reinforcement is more, what happens is your material that you're producing can withstand high load. Okay, at the same time, if your matrix becomes less, okay, if you are mixing the matrix lesser when compared to your reinforcement, what happens is the reinforcement, say for example, if you are adding a fiber as a reinforcement, so if the fiber is popping out, okay, if in the case that's the case, if the fiber is popping out, so it is prone to atmospheric interaction. Okay, so it may be subjected to oxidation reaction, which leads to failure of the product. Okay, so the reinforcement volume fraction has to be considered as very important thing. So what volume you are going to use the matrix, and what volume we are going to use reinforcement, that has to be calculated very effectively. The next thing is matrix properties, including effects of porosity. So porosity has to be considered here. So reinforcement matrix interface properties and the residual stress arising from the thermal and mechanical history of the composite. Okay, so a possible degradation of the reinforcement resulting from mechanical reaction. Degradation in the sense the material is subjected to shrink. Okay, so after manufacturing material, what happens is it is subjected to shrinkage when it is subjected to solidification. Okay, so you'll be using this type of matrix in a liquid form. Okay, so your metal will be in a liquid form. So when it is solidified, what happens, your area becomes small. Okay, it will get quite shrink, when compared to that of your other matrix. Okay, so this is predominantly happening only in the case of MMCs. The shrinkage will happen only in the case of MMCs. So next we have the some of the processings of MMCs. So today we will be discussing about the liquid state properties. Okay, liquid state processing methods. And in liquid state processing methods, we have stir casting, infiltration, gas pressure infiltration, squeeze casting, and pressure dye infiltration methods. Okay, so stir casting is nothing but you would have studied in your manufacturing technology one. So it is done by mechanical stirring. Stirring is nothing but you're going to stir with a stirrer. It has to be continued for a period of time, so the metal will continue staying in the liquid state. Okay, so infiltration is should be added. Okay, so then we have a distribution of dispersed phase throughout the matrix is not perfectly homogeneous. Okay, so if you are not distributing the material in an effective way, so if you are not mixing it thoroughly, what happens, the matrix won't stick onto the reinforcement and it doesn't becomes a homogeneous mixture. So that is what they are discussing here. There are local clouds of dispersed particles, and there are many gravity strengthened of dispersed phase due to a difference in the densities and dispersed and matrix phase. Okay, so these are the disadvantages in the stir casting method. Okay, so let us see let us try to understand with the help of this particular diagram. Okay, so this is a flow chart that is happening in the case of chip casting. So first thing is melting of matrix material. Okay, so first thing what you are going to do is you have to melt the matrix material. So what does it mean? This, so here you are going to use the matrix material in the form of solid state. Okay, so solid state material is used here. That solid state has to be converted into liquid. So it means that melting of matrix material means that the solid material has to be converted into liquid state. Okay, so see, stirring of molten metal by mechanical stirrer. Okay, so here first thing is you are going to melt the metal. Then the next thing is what you are going to do is you have to stir the material. Okay, so stirring helps in mixing of material. Okay, so what happens is it does not allow the material to solidify. Okay, if you are just adding heat, there might be a possibility for the molten metal to get solidified. Okay, so in order to remove that difficulty, in order to eliminate that difficulty, what you are going to do is you have to start stirring the molten metal continuously. Okay, so it is not done vigorously, it will be gradually done. Okay, the next thing is feeding of reinforcement material. So this is where you are going to add your reinforcement material, either in the form of particles or in the form of flakes, or you can add it in the form of granules also. Okay, so predominantly they will be using dispersed phase. Dispersed phase is nothing but a powdered state. Okay, so reinforcement is added over here. So continuous stirring of mixture matrix plus reinforcement happens in the next stage. Okay, so here the stirring is not going to stop. Okay, when you are pouring the material also, when you are putting your reinforcement inside your container, then also the stirring has not to be stopped. Okay, the stirring has to be continued till the complete mixing is being done. Okay, the next stage is pouring of mixture into the mold. So we have some molding methods also. So we have what to say, hot chamber die casting, we have cold chamber die casting, and we have some shell casting methods also, and investment casting. Any method, okay, any method can be used after this thing. Okay, so for providing a shape to your mixture, what you are going to do is you have to pour the material into a mold, and finally you have to allow the material to solidify, so in order to obtain a usable product. Okay, so this is what happens in stir casting method. Let us discuss once again. So let us discuss these points alone. Okay, the first thing is melting of material in order to convert the solid material into liquid state, and the stirring has to be. I'm sorry. So next, the stirring has to be continued until the feeding of reinforcement is done. Then the continuous stirring has to be done for a period of time, so that the mixture becomes a homogeneous mixture. And then once the mixture is converted into a homogeneous mixture, you are going to pour it into a molding wok, and finally you are going to allow it to solidify, so that you can obtain a usable product. Okay, so let us see the next thing. So we have infiltration. So this is the next step. The first method is stir casting method. The next method is infiltration method. So infiltration is a liquid state method of composite material fabrication, in which a preferred dispersed phase is soaked in a molten matrix metal. Okay, so you can see over here, it is soaked. Soaked is nothing but you are going to uh, what to say, you are going to inject, you are going to send the molten metal into your matrix metal. So here you can see the matrix is in the form of metal. So metal means it is in a solid state, whereas whereas your reinforcement has to be converted into liquid state, and that reinforcement has to be injected into your matrix metal, which fills the space between the dispersed phase inclusion. Okay, let me read this point again. Infiltration is a liquid state method of composite material fabrication, in which a preformed dispersed phase, maybe ceramic particles, fibers, oven, is soaked in a molten metal matrix. So what we are going to do is the dispersed phase of reinforcement is getting soaked into a metal matrix, which fills the space between the dispersed phase inclusion. Okay, we'll try to understand with the help of diagrams in the next slide. So listen to the next point here. The motive force of an infiltration process may be either capillary force. The first thing is by capillary action, it may get infiltrated by itself, or it can use either external pressure. Okay, external pressure may be a gaseous gas pressure, or mechanical pressure, or electromagnetic, centrifugal, or ultrasonic pressure. Okay, so yeah, it is subjected either to pressure, or it can just enter into your matrix metal with the help of capillary force. Okay, okay. So let us see gas pressure infiltration method over here. So gas pressure infiltration is a forced infiltration. It is a forced infiltration. It is not happening on its own. Okay, so what you are going to do is you have to force the molten metal into your preform with the help of gas pressure. Okay, it is an artificial method. It is not going to happen with the help of capillary action. So let us see what is happening here. So gas pressure infiltration is a forced infiltration method of liquid phase fabrication of metal matrix composites using a pressurized gas for applying pressure. Okay, so you can see from this particular diagram, you can see, so the green color portion becomes your preform, and the red color portion is your molten metal. So what you are going to do is, when you are putting the molten metal, the density of the molten metal is higher, so that it won't get infiltrated in this particular dots. Okay, you can see some yellow dots over here. Okay, so the yellow dots is nothing but your gap into which your molten metal has to be infiltrated. Okay, so since the density of your molten metal is higher, it is quite difficult to infiltrate the preform. So what we are going to do is we are going to use gas pressure. So here you are going to use nitrogen gas. Okay, so you can see here pressurized gas for applying pressure on the molten metal by forcing it to penetrate into a preform dispersed phase. So preform is a dispersed phase over here, and here you can see some yellow dots. So what you are going to do is you are going to add gas pressure from the top. So you have a small deck provided over here. I mean, duct is provided over here. So through the duct, what you are going to do is you are going to inject N2 gas, high pressure nitrogen gas has to be sent through this duct. So what happens? Due to that pressure, this molten metal will get infiltrated into this material. So here here initially it is considered as a preform, but here in the next picture on the right hand side, what we are going to do is we are done with infiltration. Okay, and that is why it becomes metal matrix composite. Okay, so gas pressure infiltration method is used for manufacturing large composite parts. Okay, so even a very big part can be converted into a metal matrix with the help of this particular thing, gas pressure infiltration. The method allows using non-coated fibers due to short contact time of fibers with the hot metal. Okay, so this is the next advantage of using gas pressure infiltration. The next thing is in contrast to the method using mechanical forces, gas pressure infiltration results in low damage of the fibers. So what happens is, so if you are using any other method for infiltrating the molten metal, uh, gas pressure produces better results when compared to that of other things, because when you're applying, say for example, if you are adding a die over here, die on the top, and with that die, what happens is the die is subjected to move downwards, so that your pressure is getting transferred to the molten metal and it comes down. So what may happen is it may damage the walls. Okay, since the pressure increases, what happens? The walls is subjected to pressure, and it may get cracked up. Okay, so gas pressure means it is what to say, it is evenly spread in all the areas, so that the infiltration method can be completed very soon and in an effective way. So that is what we have seen as gas pressure infiltration. So next thing is squeeze casting infiltration. So squeeze casting is nothing but you are going to apply a squeezing pressure. Okay, nothing but if you are just consider that you are squeezing your lemon or something. Okay, the same thing is going to happen here. So the diagram is quite similar to that of your previous slide, but the only thing is we have an upper die and a lower die here. Okay, so here we have a what to say, we have a closed, it is happening completely in a confined environment, whereas here it is subjected to open environment. Okay, so let us see what squeeze casting infiltration is all about. So it is a forced infiltration method of liquid phase fabrication of metal matrix composites using a movable mold part. So here we have a ram. So the ram is subjected to apply pressure on the molten metal. For applying pressure on the molten metal and forcing it to penetrate into a preformed dispersed phase placed into a lower fixed mold half. So we have a lower half and an upper half. So in the upper half we have the RAM. Okay, so upper half we have the RAM, and in the lower half we have a provision for containing your preform and also your matrix material. I mean your molten metal. Okay, the squeeze casting infiltration method is similar to that of squeezing casting techniques used for metal alloy casting. So let us try to understand from this particular diagram. So we have an upper half and a lower half. The lower half provides the space to place to accommodate your preform and a molten material. Okay, I mean the molten metal. So what happens is, after this particular thing is done, the upper movable half will come down, so that this pressure, the downward pressure will get acted upon to this molten material. I mean the molten metal. So what happens? Due to that pressure, it will get infiltrated, and this preform will be converted into a metal matrix composite. So this is what's happening in the case of squeeze casting. Okay, so in gas casting we are using gas pressure, whereas in squeeze casting we are using the pressure of the ram in order to infiltrate the molten metal into your preform. Okay. Right. So next thing is squeeze gas infiltration. We have some steps over here. Squeeze casting infiltration process has the following steps. A preform of dispersed phase is placed into the lower mold of the half. So lower mold half contains your preform. A molten metal is a predetermined amount is poured into the lower mold half cavity. So first thing is, you are going to place the preform, over which you are going to add your reinforcement metal in the form of molten state. Okay, the upper movable mold half moves downwards and force the liquid to infiltrate the preform. So what happens is, you are going to move the ram from the top, so that your molten metal will get infiltrated into your preform. The infiltrated material solidifies under the pressure. Okay, so here what you are going to do is, it is not going to stop just like that after infiltration. So what you are going to do is, you are going to apply the pressure for a particular period of time, so that it solidifies under the pressure itself. Okay, so no material is allowed to go out of the preform. Okay, the part is removed. The part is removed from the mold by means of an ejector pin. So we have an ejector pin over here, which helps in ejecting the material outside. The method is used for manufacturing simple small parts, and also automotive simple and small parts, and in predominantly they are used for automobile engine pistons from aluminum alloy, reinforcement by aluminum short fiber. So these are the things that you are using with the help of squeeze casting infiltration. And the next thing is pressure dye infiltration method. The pressure dye infiltration is a force infiltration method of liquid phase fabrication of metal matrix composites using a die casting technology. When a preformed dispersed phase is placed into a die, which is then filled with a molten metal entering the die through a sprue or a penetrating into the sprue and penetrating into the preform under the pressure of the movable piston. Okay, so here we have a molten metal in a hopper. Okay, so in this particular thing, we are having a molten metal in a hopper, and we have a fixed die and a movable die with an ejector pin over here. And within the fixed die and movable die, what we are going to do is, you are going to add the preform in this particular space provided for. This is a cavity. Okay, in this cavity, what you are going to do is, you have to put the preform inside, through which into which the molten metal has to be infiltrated. Okay, so you have a molten metal over here, and we have a plunger over here, plunger or a piston. Okay, so it can also be called as a piston. So what happens is, when the piston moves on towards the right side, what happens, this molten metal will get infiltrated into this particular area. Okay, the same thing in squeeze casting, we are going to apply the force from the top, but here we are going to apply it in a mm, horizontal direction. There it is applied in a vertical direction. Here it is applied in a horizontal direction. And since we are using a die over here, that becomes a pressure die infiltration method. Okay. Okay. Just a minute. So the next thing is we have solid state processing of MMCs. In solid state fabrication of metal matrix composites, it is a process in which the metal matrix composites are formed as a result of bonding matrix metal and dispersed phase due to a mutual diffusion occurring between them in solid state at elevated temperature at the upper pressure. So what you are going to do is here there is no need of conversion of solid into a liquid medium. Okay, so what you are going to do is you are taking a solid and your solid as your matrix, and again a solid as your reinforcement. These thing has to be combined to one another with the help of external force or something, but no heating is involved in the case of solid state processing method. So there is no conversion of a metal into a liquid. Okay, so can you understand the difference between solid state processing and liquid state processing? So in the previous thing we are discussing about the liquid state casting, infiltration method, gas pressure, and squeeze casting, and then pressure die casting. Everything we are discussing for liquid state processing, whereas in solid state processing there is no need of heating. So it is just taken in the form of solid. Your matrix is taken in the form of solid, and your reinforcement is also in the solid state. So next, what you are going to do is we are going to mix these two in order to become a composite material. The low temperature of solid state fabrication process and dispersed undesirable reaction on the boundary between the matrix and the dispersed phase. So metal matrix composites may be deformed also after stirring after sintering operation by rolling, forging, pressing, drawing, or extrusion. So sintering is nothing but by applying pressure we are going to what to say for you consider that you have four molecules, and those four molecules are subjected to external pressure. So what happens is molecule 1, 2, 3, 4 all will get combined to form a single molecule. Okay, so with a space provided in between, you'll be having a space into which your molten material can be infiltrated there. Okay, the deformation process may be either cold or hot. The recrystallization, I mean, the deformation state. The deformation state is nothing but change of phase from one state to another. Deformation is nothing but change of shape or something. Okay, so the change of shape can be done either in by using a cold working operation, or it can be a hot working operation. That depends upon the recrystallization temperature of the material that you are going to choose. Okay, so the deformation of sintering composite material with dispersed phase in the form of short fibers results in preferred orientation of fibers and anisotropy of the material property. Okay, so this also has to be considered in this. So solid state processing of MLCs, we have first thing is diffusion bonding, in which a solid state fabrication method in which a matrix in the form of foils and a dispersed phase in the form of long fibers are stacked in a particular order and then pressed at elevated temperature. So what you are going to do is you are going to add your matrix state first, then your reinforcement. So it becomes a sandwich structure. Okay, one over the other, you are going to place your reinforcement and the matrix. Okay, and then what you are going to do is you are going to apply pressure. Okay, so let us consider something in between my hands. So what happens is in this area, what in this particular area, what I'm going to do is I'm going to place your fibers and also your I mean your reinforcement and also your matrix. Then what I'm going to do is I'm going to apply the pressure over it, and also the temperature also it is going to be high. Okay. So what happens due to the temperature, the material tends to change its phase from solid to liquid, and due to the pressure, what happens is it will get sintered. Sintered is nothing but it will combine to form a single molecule. Okay. The finished laminate composite material has a multi-layer structure. So here you can see a multi-layer structure. For example, what you can consider as an example is your this one in the what to say in motor and all, we'll be having a stator, right? So those stators are manufactured with the help of sintering process. Okay, I mean diffusion bonding. It will be having a small fin-like structure. Okay, those fins are arranged in such a way that it has a very small space in between. Okay, so that thing is done with the help of diffusion bonding. Okay, diffusion bonding is used for fabricating simple shapes. Okay, this is predominantly used for making a simple shapes only. No complex shapes can be used with the help of diffusion bonding technique. Okay. The next thing is solid state sintering. We have, I mean, solid state processing. We have sintering process. So let us discuss what a sintering is all about. So sintering fabrication of metal matrix composite is the process in which powder powder of a metal matrix is mixed with the powder of dispersed phase in the form of particle or short fibers for subsequent compacting and sintering in solid state. So what you are going to do is you are having your matrix in the state of powder and also your reinforcement in state of powder. What you are going to do is you are going to apply the pressure from the both ends, so it gets converted into a single molecule. Okay, so let us have the definition. We are having the definition over here. So sintering is the method involving consideration of powder grain consolidation of powder grains by heating the green compact part to a high temperature below the melting point when the material of the separate particle diffuse to the neighboring powder particle. So what happens is you are going to apply the pressure on one single material. So what happens there is it diffuses with the with the nearest material. Okay, you are going to add pressure on one material, so the next subsequent material will get diffused with the parent material. Okay, that is what the initial material. That is what happening in the case of sintering. In contrast to the liquid state fabrication of metal matrix composites, sintering methods allow obtaining material containing up to 50% of displaced state. Okay, so in the case of liquid matrix, in the case of liquid state processing, what we have end up in mixing the reinforcement is only 30% of reinforcement in the form of dispersed state can be mixed in the case of liquid state processing. Whereas in the case of solid state processing, it provides an ability to have up to 50% of dispersed state with your matrix. Okay, so 50% of reinforcement can be mixed with your matrix material. Okay, so that is what the major advantages when compared to the top your solid state, liquid state processing method. Okay, so next we have solid state processing methods. We have three different methods. The first thing is hot pressing fabrication of mathematical composites, hot isostatic pressing fabrication of mathematical composites, and hot powder extrusion fabrication of mathematical composites. Let us discuss one by one over here. So here in this case, it is just like your pressing or coining operation. Okay, it is just similar to that of pressing or coining operation. So you can see a powder is arranged in this particular area, in which we have an upper punch and a lower punch. Lower punch is immovable punch, and upper punch is a movable punch. So what happens is we are going to apply heat on this die. So you can see the change in color. So here it is black color, and here it is in red color. So red color means you are going to apply heat to the die. Okay, so here it becomes a hot die. So what happens is you are going to apply pressure from the top and heat on the other side. So this is a cross section. Okay, it is not a complete section; it's a cross section. So what happens is it's getting converted into a composite material under a confined environment. Okay, so it is happening under a closed environment. So this is the first part. So initially, what you are going to do is you are going to add powders in this particular space provided here. So then what happens is the space is limited. Okay, the space is completely we are going to reduce the space by moving the upper punch. So what happens from the upward direction, a pressure is being applied. So pressure is applied in vertical direction, and the heat is applied all towards in 360. Okay, so everywhere heat is applied, so it becomes a homogeneous mixture. Okay, so after that, what you are going to do is you are going to move the upper punch up, and you are going to take the product outside. Okay. So here you can see a combination of pressure and temperature is added in order to convert a product into a composite material. Okay. So here it is not only the matrix is being added in this particular thing. So powder means what does it mean is you are going to add your matrix material and as well as your reinforcement. Both is added over here. Okay. So in the previous thing, in the liquid state of fabrication, what did we see? The matrix is being added in this particular space, to which your molten material is then added with the help of infiltration method. Okay, but in this case, what you are going to do is you are going to convert your matrix and also your reinforcement in the form of dispersed state, that is your powder, and then we are going to apply pressure and temperature in order to convert it into a usable product. Okay, the next thing is hot isostatic pressing. Isostatic pressing is also similar to that of the previous thing. So fabrication of metal matrix composites sintering under pressure applied from multiple directions. So here, this previous slide, so we have pressure from a single direction, only from the upward direction. But here, in all directions, the pressure is being applied. So let us see what is happening. Okay, so sintering under a pressure applied from multiple directions through a liquid or gas medium surrounding the compact part at an elevated temperature. So what happens is So this thing, okay, this thing, what we are going to do is we are going to add gas into it, okay. Whereas this particular thing, that is the outer surrounding, which is represented in gray color, what it is? It is a steel can container. So steel can container is nothing but can is a flexible medium. Okay, so it may be a like your Coca-Cola or beverage tin. Okay, just like that. So into which what we are going to do is you are going to add the powder over here. Okay, so this is the powder. Powder is a mixture of what? Your reinforcement and also your matrix. So what you are going to do is you are going to put in your powder in this particular area, and in order to apply pressure on all areas, okay, in multiple direction, what you are going to do is you are going to use gas pressure. So this is the thing. This is the surrounding, and into which the gas pressure is being infiltrated, and the pressure is applied in all direction in an even manner. Okay, so the product is completely surrounded with pressure, and also this is completely happening in a closed chamber which is subjected to heat. So here you can see a heated chamber. Okay, so heat is applied from one end and pressure is applied on all the other directions. Okay, so in order to what to say, in order to distribute the pressure evenly in all directions, you are going to use a gas, and predominantly we will be using an argon gas in the case of isostatic. Okay, so the next thing is hot powder extrusion fabrication method. This is similar to that of your extrusion method that we have seen in manufacturing technology one. Okay, so here we have a billet. Billet is nothing but a powder. So into which we have a forward extrusion and also reverse extrusion gap. So the first thing is we are going to talk about forward extrusion, and the next thing is reverse extrusion. So we can see here. So what we are going to do is the RAM is actuated in a horizontal manner. So we have a small space provided here into which your powder is being poured. I mean, powder is a mixture of your reinforcement and the matrix is being deposited in this particular. I mean, it's not deposited; it is just put in this particular area, and we have a die opening over here through which the material will come out. Okay. So what you are going to do is initially what you are going here, this is hot powder. Okay, so we can see the term over here. Hot powder is nothing but you are not going to apply heat in this particular area. This container is not subjected to heat. Okay, so what you are going to do is you are going to heat the powder well in advance before the powder is put into this container. Okay, so in this particular in these two categories we saw about heat and pressure is applied in the, it is an integral part of the machine. Okay, whereas in this particular thing the powder is subjected to heat in some other area, and that heated powder is brought into this particular container, and with the help of ram and the die opening we are going to extrude the part. Okay, so the die can contain shape, the final shape of the product. Okay, so the die opening will be having a shape through which your material will come out. Okay, so if the die opening is of circular shape, it will be end up in producing a circular component. If it is of a square shape or a bar like structure, we will be end up in producing a bar. Okay, so this is the forward extrusion, and this thing we can see the ram is here and the die is over here. And in this particular thing, this is considered to be as an indirect extrusion, whereas your RAM contains your die. Okay, here you can see die is this particular thing. Okay, so what you are going to do is you are going to push the RAM on the right hand side, whereas your material will come out on the left hand side. So since your die opening is here, the die becomes an integral part of the RAM. So this thing is okay. So can you understand what you have discussed? So let us see. We have thought about, we have discussed about the uh, metal matrix composite manufacturing method. So we have discussed about what is metal matrix, and we have seen some tips in order to processing metal matrix. We have liquid state processing and solid state processing. In liquid state, we are discussing about stir casting, infiltration, gas pressure infiltration, squeeze pressure, and die infiltration. Whereas in the case of solid state processing, we discussed about what to say, I mean, as a diffusion bonding, filtering, and also pressing operation. Okay. So in pressing operation, we have three different types of pressing: hot pressing fabrication, hot hydrostatic pressure, and hot powder extrusion. So these are all the things we discuss in this particular class. Okay. So thank you very much for attending the class. We'll meet up in the next class for the next topic. We'll be discussing about ceramic matrix. Thank you. Thank you.